The network classes table I talked about is here on the slide in front of you. You can see we have 5 classes, class A, B, C, D, and E. Those are going to be on the extreme left. The range of the first octet, which is that first of the 4 boxes we were just looking at, is listed in the table here. We have a 1 to 127 range for class A, but we have a little asterisk at the end of class A, as you can see. We have a little note at the bottom of the table there. 127 equals loopback adapter on the local host. We'll talk about that in just a second. And then we have the number of network octets, and the number of hosts in the network is, in this case, just over 16 million, almost 17 million approximately if we round up. So class A, class B, class C, class D, and class E. Class A, B, and C are the classes that we use most often. We use them in production every day. We run networks on them all the time. And we have dedicated private IP address ranges in each one of them. And we'll use those internally on our LAN. And we have publicly available IP addresses in each one of them. We'll use those externally on our WANs. And that's how we're going to be able to set up and communicate. The 127 address, although it is legitimately part of a Class A address block, it is considered part of the Class A, is a special address. It's what we call a set-aside address block. The 127 address block, the entire block, is not used for network communications between machines, but rather is used specifically to be able to do diagnostic work on the machine. So 127 is actually going to be 127.0.0.1, which is our loopback adapter. And you probably, I'm sure, are familiar with that, at least hopefully you are. Loopback adapter address is going to be 127.0.0.1. So we just want to know when we see 127.0.0.1 that is actually going to be the loopback adapter. And so if we ping 127.0.0.1, we actually are pinging the network card of our local machine, and we're checking to make sure it's powered on, it's connected, it's working correctly. It's a diagnostic address, in other words, right? We could ping the address assigned to the network card, 192.168.01 or whatever it may be, and if we get a response back, we know automatically that the card is connected and working. We're bypassing the loopback by pinging the IP that's assigned to the interface. We kind of combine both tests in one. If we started by pinging the loopback, we know the card is powered on, but we don't know whether the IP interface is actually got a valid IP address. That would be the next stop in the troubleshooting train. And by pinging that IP address, 192.168.0.1 or whatever, we would then obviously understand that as well. So just to understand that although we classify 127 as a Class A address on paper, we really think about the first octet range as being from 1 to 126, because that's the operational range that we can use in terms of assigning IP addresses. And then we have 128 to 191 for Class B, 192 to 223 for Class C. Class D, 224 to 239 is the multicast range. That's used for multicasting. Multicasting is used for things like streaming media, desktop imaging, things of that nature. And then Class E, 240 to 255 is typically referred to as the experimental range. It's the range that's set aside for using experimental technologies. IPv6 was tested in that range at one point before we moved into the full IPv6 solution that we use today. And there are other things that may or may not be going on in that range. But we don't tend to assign those addresses unless we're involved in using one of those specific technologies or projects that may be tested or be used in those ranges. So typically we stick from the Class A through Class D range, 1 through, with the exception of 127, through 239 for our first octet. Remember, the middle 2 octets, anything from 0 to 255, and the final octet, anything from 1 to 254. So having said that, the number of network octets is the number of octets that we are going to be specifying are used to describe the network we connect to. The remaining number of octets, if we have 1 octet for the network, total of 4 octets, the remaining 3 octets are representing the number of hosts uniquely that can exist within that network. So in a Class A network, we have 1 octet for the network. That means we have 3 for the hosts. We put a 3 there with an H for the host. What that would mean is that in a Class A address, let's say starting with octet number 1, we would do something like 1 dot, and this 1 right here, this first octet, we're going to put an N above this. This is our network octet. And then the remaining octets, let's say 0, 0, 1, over here, these 3 octets, going to put an H above them. These 3 octets represent the host. And by differentiating between the network and the host, and oops, we forgot, got to put our little dots in there to make sure we're official. By representing and differentiating between the network and the host, what we're effectively doing is allowing us to be able to see which component of the IP address represents our network association, which part represents the individual host ID. So on the one dot network, 001 is a unique host, 002 is a unique host, 003 is a unique host, 255.254.255 is a unique host. All of them are unique hosts within the one dot network. In the two dot network, new network, 001 is also a unique host. 2.001 is different from 1.001. Both hosts have a 001 ID, but one host is associated with the .1 network, one host is associated with the .2 network. As a result, they are different. They are unique. And that's why we need to understand what is the network portion of the address, what is the host portion of the address. When we have two octets given over to the network, so the next one down, class B, has 2, or class C, which has 3. Let me just change colors here so we can keep track of that. Let's do class 3. And let's go ahead and let's use 192. We'll do that one right down here, right? So if it's going to be the first 3 octets, then what we're going to do is we're going to do 192. As soon as I can learn how to make a circle, there we go. 192. And let's do 01. And we're going to put a box across these 3 right here. And we'll do it on the bottom this time instead of on the top. Put N for network. We'll put our dots there representing that, right? And then our last one over here, put a box over here. And we'll put, let's just say 2. And that's going to be a host address. And so in the Class C address of 192.0.1, the first 3 octets are network. So in the 192.0.1 network, .2 is an individual host, .3 is an individual host, .4 is an individual host. When I go to the 192.0.2 network, and I have .2 host, .3 host, .4 host, those are all unique hosts. They are different from the hosts in 192.0.1 because 192.0.1 is a different network from 192.0.2. Again, important to understand and differentiate so we can tell that each host is unique. We have only 254 hosts in a Class C network because the host range on the last octet is from 1 to 254. We have approximately 16.8 million hosts in a Class A network because the host range is 001, 002, 003, all the way from 001 up to 255, 255, 254. Add them all up, you get approximately 16.8 million individual hosts per network. But we have only 126 networks in the Class A range. So we have to understand that as we add one area and increase size in one, we decrease the other. You'll notice that we have a very small number of networks in Class A because the range is really from 1 to 126, but a very large number of hosts. When we go up, we have in Class B or Class C, Class B has 2 octets, 128.0, 128.1, 128.2, from 128.0 all the way from 128.0 to 128.255, right? And then we go to 129, and we do 129.0 all the way to 129.255. So when we add up all those networks from 128.0 to 191.255, we got a lot more networks than 126. But because we got a lot more networks, we got a lot fewer hosts. We only get about 65,000 hosts per network because we've increased the number of networks. We've taken one of those octets and moved it over and given it to the network side instead of leaving it with the hosts. We've decreased the number of hosts, but we've increased the number of networks. It's a zero-sum solution. That total number of IP addresses that exist that are unique cannot be in any way modified, meaning we have only a certain amount of networks and a certain amount of hosts. How we carve that up is up to us. More networks, less hosts, right? Less networks, more hosts. We could find a happy medium somewhere between the two as well. But as we increase the number of networks, we decrease the number of hosts per network. And that's why at the bottom here in Class C, we wind up with 254 hosts. because we have a very large number of networks from 192.0.0 to 223.255.255. That's just over 2 million networks. But in those 2 million networks, each network can have exactly 254 unique hosts per network. So we want to make sure we understand network classes. This is also very important and something that's foundational and elemental about our ability to understand how to network, how to use IP addresses, how to understand how class-based networking works, and most importantly, how to apply and use the concepts of IP addresses and IP networking to understand how to manage our networks and send and receive information. All of this information is kind of buried, waiting to be discovered here in our table. It's very important for you to have a good understanding of everything we've been through here. Might be another good place for you to pause, take a couple of quiet minutes, reflect on all the stuff we've been discussing, perhaps rewind and watch our discussion again, listen to it, make some notes before we move on. That way, in case you have anything that's a little fuzzy, make sure you capture it all and it's all straight in your head before we continue.